Everybody. We're going to look at limits and continuity. So just briefly, the intuitive idea of a limit is if we've got a function, so like here we've got this f of x, and it is defined on an open interval about x equals c. So we're thinking of this function as being pretty nicely behaved around some particular x value, and they tell us it's going to be c that we care about. And we can look at the function. Even though there's a hole right at c, the function itself is smooth. It's no corners, no asymptotes. So we've satisfied this first bit. An open interval, that just means like a neighborhood. If we have this function, so if this is f of x, and here's c, so that this is f of c, we would say that a neighborhood around an open interval around x equals c, that's just going to be, so open, that means that rounded endpoints, we don't include the endpoints. And we're just looking at a close area at f of c and values of the function above that and values of the function below it. And in order for this limit to exist, we need to be able to approach from below or from the left. So here this is below or left. So as we're getting x values that get closer and closer to c, we're looking at f of x values that get closer and closer to f of c. So we're on this purple arrow. You can see that even though this is not defined, f of c is not defined because there's a circle with nothing filled in, then I can still get as close as I want. If this value was 5, say, I can go to 4.9999999, etc. So the value of the limit from the left, and we use this notation. Let me write it in a bigger page. So the limit from the left or from below uses the notation minus. So I've got the limit as x approaches c, and then we're going to put something that looks like an exponent, but it is not an exponent. So this little minus sign here, that tells us that this is from the left. This is the limit as x approaches c from below or from the left of f of x. Well, let's look at the graph. As we get closer and closer to x equals c, the function value gets closer and closer to L. So we would say that the value of the limit as x approaches c from below or from the left of x of x is equal to L. We also need to look at the limit as x approaches c from above or from the right. So let's write that down. If we have the limit as x approaches c from the left, from the right, or from above, we would write it this way. The limit as x approaches c, and again, this is in the position of an exponent, but it is not an exponent. This plus says I'm approaching c from values of x that are above c. So I'm looking at values of x that are bigger than c, so they are to the right of c or above c. And now I'm going to look at values of the function for those same values of x. So we're up here, and I can see for this graph, we definitely approach L from the right. So just in this simple image, I can see that if I approach x equals c, and I go along the graph, so here's x, here's f of x, that even though f of c is a whole, is not defined, we still are getting as close as we want to the y value L, and from above and below. And that is exactly what it means for the limit to exist. If the limit from below equals the limit from above equals some number L, so we're thinking it's not infinite, then the limit as x approaches c with no little plus or minus of f of x is equal to L. So even though f of c is not defined, the limit as x approaches c with no plus or minus of f of x is defined and equals the number L. We're looking at, in this assignment, we're looking at two things. We're looking at the intuitive idea of limit and the intuitive idea of continuity. And the simplest way I can describe continuity is if you can trace a graph without having to pick up your finger, then it is continuous. But let's check this out. In order to trace f of x here, I have to pick up my finger, pardon me, at this hole. So f of x is not continuous at x equals c. We have to pick up our finger. The kind of discontinuity is a hole. There is a hole. We don't mind holes so much because we can plug them. I can make a new function. So let's see. This was f of x. Let's create a new function, capital F of x, and it's going to be equal to f of x if x isn't c. So it's going to be exactly this graph, but when x is equal to c, pardon me, if x is equal to c, the function is going to be equal to L. And that is a way that we can take our function and kind of repair it. So this kind of discontinuity, this hole, is not so bad. We can plug that hole and work with the function. Well, let's look at a couple of other simple functions. We call these functions that have parts that seem to be disconnected. We call these piecewise defined functions. So the first piece, I can see that it's some kind of function that is going down. And let's look at the limit as x approaches -3. Let's see where we are. Here's -3. The limit as x approaches -3 from below. So the negative in front means the -3. The negative afterward means from the left or from below. So we're on this green part. Actually, I should be doing this in green. So let's see. We've got the limit as x approaches -3 from below of f of x. As x gets close to, so we're looking at it this way. As x gets close to -3, the function gets close to the y value -2. So we would say that the limit as x approaches -3 from the left of f of x is equal to -2. Well, what about the limit from above, or the limit from the left? Pardon me, from the right. Okay, we want pink. There we go. So we're on this part of the graph now. And this is going uphill. This is an increasing function. But we're kind of looking at it backward. We're going along the x-axis, plugging in x values that are greater than -3, and we want to see what happens to the function at those x values. So we're here, we're going along here, and I can see that I will get as close as I want to the y value -3. So I would write the limit as x approaches -3 from the right of f of x is equal to -3. Let's also write down the value of the function. So let's see. What is f of -3? So see, the open or empty circle is the value that is not included. The filled in circle is the value that is included. So this dot is the value of f of -3. So f of -3 is equal to -2. Since the two limits are different, since the limit as x approaches -3 from the right isn't equal to the limit as x approaches -3 from the left, then the limit, well, let's write it properly. The limit as x approaches -3 of f of x, with no plus or minus on the -3, does not exist. And we write does not exist, D N E, does not exist. So this has no value. The limit has no value. The function does have a value, and the right limit, the right limit has a value, and the left limit has a value. Let's look at this graph. If I'm tracing it with my finger, and I'm on this upper part, and I want to go to the next section, I have to pick up my finger. There's no way to go from one part to the other without picking up my finger. So this is not continuous. And one of the official ways that we can say it's not continuous is that the limit doesn't exist. If the limit doesn't exist at a particular x value, then there's no way that that function can be continuous. This is what we call a jump discontinuity. This is a jump discontinuity, because in order to go from one part of the function to the next part, I have to lift my finger or lift my pen and move to the next. So we have a whole discontinuity, a jump discontinuity, and an asymptotic discontinuity. As we approach zero from below, do you see that we don't even have the situation of a jump? So here we are. Let's make better color. Here we go. We're coming up here, getting closer and closer and closer to x equals 0 from below. I can see that the function values are going to infinity, to positive infinity. So since infinity is not a number, infinity is an idea of as big as we can get. There's no jump here. Even though this second part of the function is a nice little, it doesn't have an asymptote. Oh, asymptote. It's a lovely word. Asymptote. It's one of the best words in the world because it uses, you say almost every letter. Asymptote. Beautiful. And it just means that a function goes off to positive infinity or to negative infinity. So this kind of discontinuity, let me cheat just a second. I hope y'all are doing well. I'm just hanging out at my house playing with calculus, which is pretty lovely, I have to say. Here we go. So we have the whole discontinuity, the jump discontinuity, and the infinite discontinuity, where we have some kind of vertical asymptote. We think of a whole discontinuity as removable because we can repair the function, just like we did here for the earlier function. We created a new function that repaired little f of x when x was equal to c. So when x is c, we get the value L. So now we've got this function that is behaved. no hole anymore. So we've got this function with no hole anymore. So that's the lovely thing about holes. They are removable and repairable. Even when you're doing something with engineering, you can repair a function if it has a hole. If it has a jump, then the two parts of the function are physically apart. And although you can translate one part up or the other down, that's a huge change to a system. So a jump discontinuity can be repaired, but it's difficult. An infinite discontinuity cannot be repaired. You have to change the system. I've got it ahead of myself. Here we go. Example 1. So we're going to look at this graph. And I want to make sure that I use the correct colors.